So next we have Lily Wang, who's the science lead at OpenForceField, and she'll be talking to us about some updates from OpenForceField and how that pertains to free energy calculations.
Cool. Thank you, Megan. I'd like to start off just by thanking the conference organizers who've put together this amazing event, and thank you for giving me the opportunity to present here. It's my first time at Alchemistry, and I've been really enjoying every moment. It's been great. So today, I'd like to talk to you a bit about OpenForceField and some recent progress that we've made in force field development, and focusing specifically on some projects that we have and how they relate to free energy simulations that use our force fields. So for those of you who don't know who we are, OpenForceField is much like Open Free Energy in the sense that we're a consortium of people from academia and industry who've come together in a pre-competitive partnership with the shared mission of building bigger and better force fields. Yeah, sorry for the cracking. I'm not sure why that's happening. Oh, it's my earring. Oh, that's it. Can I shift this somehow? Is this helping? Okay. Yeah? Okay, fantastic. So yeah, continuing on, much like Open Free Energy, we also have a fundamental commitment to being open. So all software and data sets that we create and generate, we release permissively with licenses like MIT and CC BY. Just a bit of history of OpenForceField. So the seeds of what would eventually become OpenFF were first laid in 2016 when Chris Bailey arrived at UC Irvine and laid the scientific groundwork for what would eventually become the project. His work resulted in the release of the Smirnov format, which, as shown on the previous slide, allows us to assign force field parameters to molecules using direct chemical perception, as shown here, and bypassing the need to define formal atom types. In 2017, we published the first force field that used this format, Smirnov 99 Frost, and that was a small molecule force field that descends from both amber Palm 99 and Palm 99 Frost. The next few releases that we made, starting with Parsley 1.0 in 2019, focused on refitting bond, angle, and proper torsion parameters to a growing corpus of quantum chemistry data. In 2021, we refit non-bonded parameters for the first time, in the sense that we refit van der Waals terms to condensed phase simulations. And I should note that the main lead and driver behind this project, Simon, is here today in the audience, and he's done a fantastic job. So in benchmarks, comparing Sage 2.0 to previous force fields, in this case 1.0 Parsley, we see that the van der Waals parameter refit generally improved performance across protein ligand binding for energy calculations. Since Sage 2.0, we've put out 2 more force field releases. So Sage 2.1 in the past year and Sage 2.2 this year. And both of these have further focused on updating our valence terms. And we refit improper torsions for the first time in Sage 2.1. In general, when we just do only updates to valence parameters, we don't typically expect a lot of impact on free energy simulations. And indeed, in a smaller benchmark of protein ligand binding free energies, we see essentially the same performance. And many thanks to Irfan and Megan for running these simulations. So that brings us to today. Now I'd like to talk a bit about some projects that we have in the current pipeline that we've been working on in the past year that have maybe more of an impact on free energy simulations. And we can broadly classify that impact in 2 categories. So one is the one that everyone wants. This actually affects performance, and what we hope is things to the right-hand side of this axis will actually improve results in free energy simulations. But the other way we can improve free energy simulations is just by making it easier, or possibly less easy, to set up and run a simulation. So valence parameter updates, for example, they would sit roughly at the origin of this graph. While they have improved the force field in many ways, we don't typically see any impact on the free energy benchmarks that we've run. And they don't make it any easier or harder to run simulations compared to our previous force fields. I have 3 projects that do depart from this origin a bit. So today, I'd like to talk about our protein force field effort, our neural network charge model for assigning partial charges, and touch on a bit on a project to add virtual sites to our force fields. And I'll explain why everything is where they are as I get to the project. So starting off with the protein force field, up until now, all our force fields have just targeted small molecules, and our expansion into proteins is our first foray into the wider world of more fun chemistries. This project is being led and championed by Chip and Kavanagh at the Gilson Lab at UCSD. And the general goals we have for this force field are firstly, of course, to have parameters covering both proteins and small molecules, to co-optimize these parameters so that they're self-consistent, to achieve similar accuracy, at least to start with, to existing force fields such as AMBER 14SB, to remain maximally similar to small molecule parameters, again, at least for this initial effort. And as part of this specific investigation, to see if we need to add protein-specific torsions covering the backbone and side chain structures, or if our existing small molecule parameters can generalize to wider areas of chemistry. And Chapin has been pursuing fits along both these directions, and he's named force fields where we do add protein-specific torsions specific, and he's named force fields where we don't have these null for the null hypothesis. So this is a project that's still ongoing. I'm just going to show a brief overview of the fitting workflow that we've been using. And I'll start off by explaining how we're handling electrostatics. The canonical charge model we use for small molecules is AM1BCC, and specifically we fit our force fields using the OpenEye implementation and the ELF10 variation. And the reason we use ELF10 is because, as covered previously in this conference, AM1BCC has the unfortunate disadvantage of having some complement dependence in how it assigns charges. So ELF10 averages charges across up to 10 structurally diverse conformants that have been selected to have low electrostatic interaction energies. Another downside of using quantum chemistry-based charge methods, even semi-empirical ones, is obviously that they don't extend well to larger molecules. So while that works well with small molecules, we just needed to come up with another solution for proteins. And at least initially, Chapin is following a solution that many other protein force fields do, which is to pre-compute charges and encode them in the force field. And he does that using a structure that we call library charges. Once we have these electrostatics, we go into a bonded refit, a refit of our bonded terms, and we train these both to our existing small molecule quantum chemistry data, as well as additional data generated specifically to cover peptides and proteins. I'm being quite vague about exactly how we fit to this data, and that's because we're still trying to work out what gives us the best results, and we've been varying a lot of different factors into how we train to these targets. Once we have a candidate that's been fit to this data, we put it through a number of benchmarks. If it doesn't have acceptable performance, we go back here and we try again. And we're still kind of in this phase. Once we do have an acceptable candidate, we'll move on. We'll keep going with the fitting workflow. But for now, we've spent a while trying to work out how to get acceptable performance on these benchmarks. So just for a brief summary of what's going on and why we're stuck, probably the shortest way to explain this is that our Smirnov force field candidates have some issues with secondary structure. So one of the key benchmarks that we run is just to simulate a folded protein in water on a long timescale simulation. And the idea is just to check that the protein remains stable and nothing too terrible happens. So using AMBER 14SB as a reference, that does fine with this GB3 protein. Everything remains pretty stable. But when we try and put one of our force field candidates through it, and this is one of our older ones, 0.0.2, in at least one replicate of each benchmark for null and specific, we see that this alpha helix, a portion of it uncoils into a random loop. This is somewhat water model specific, so this was done with TIP3P water. But we see that with OPC water, the behavior is slightly different. So AMBER still keeps the protein stable in solution with OPC water, and our force field candidates keep the alpha helix stable with OPC water. But what we see instead is that on the other side, the beta hairpin starts fraying instead. So this can be briefly summarized with this graph on the left here showing scalar couplings. AMBER remains pretty robust across different water models in simulating GB3. But for each of our null and specific 0.0.2 force fields, we see issues with secondary structure. Another key benchmark that we run as part of evaluating our candidates is to try and fold a 15 residue long peptide chain into a helical coil. So this is something else that amber does quite well. If you have a look at these blue diamonds, they represent the experimentally measured helical fraction across the peptide. And these other diamonds just represent different ways to calculate the helical fraction using MD simulations. So at least with the dihedral and Sparta plus methods of calculating, the curve is pretty spot on for amber 14SB, but what our candidates tend to look like is very flat, so pretty much no helix is visible in the peptide chain. And this is one of our more recent fits using the 0.0.3 protocol. So we're still struggling with this issue. We've tried a lot of things, but we have had a couple of recent breakthroughs. So very recently, for the first time ever, we had one force field candidate and one water model combination where we saw GB3 remain stable in simulation. Hooray! You might notice this is the same model and OpenC water that still shows absolutely no helix in folding the 15 residue long peptide chain. But we recently had a breakthrough there as well. So we had a different force field candidate, specific 0.0.3, start folding into the helical coil in tip 3P water. So that was really exciting to see as well. But the issue with that is that once we went back to the GB3 benchmark, it really didn't keep the secondary structure stable at all. And actually, in this case, it started unfolding both the helix and the beta hairpin. So there's some more work to do there. But yeah, once we get there, we are excited eventually to be able to use our protein force field. And the idea is once we have it, we'll be able to streamline our simulation setup workflow and be able to basically set up a simulation and export it to your favorite MD engine in less than 10 lines of code. So that's the reasoning for putting the protein force field here. We aim for it to make it somewhat easier to set up protein ligand simulations. And we also believe that co-optimizing the protein and small molecule parameters should have some benefit in accuracy. Moving on, our neural network charge model is slightly related in the sense that the motivation for wanting to use a neural network charge model arose from basically the pitfalls of M1BCC that I mentioned earlier. So namely the conformal dependence and the need to assign charges to larger molecules. Our initial goal is to basically replicate our existing M1BCC charge model. So that's why this project is on the left-hand side here. We specifically want to achieve the same performance that we currently have. And the idea is just to make it much easier to assign charges. And this project is codenamed NAGL. So the models that I'll be referring to are called NAGL throughout the presentation. I'm going to mostly skip this slide. Basically, we did a lot of experimentation into what would give us the best results. And these are the final decisions that we settled on for the 2 release candidates that we put out earlier this year. And instead, I'll just move on to showing how it works, or how well it does. So these are benchmarks comparing charges directly with the charge RMSE, as well as the RMSE of the electrostatic potential surface projected by those charges around the molecule. For all benchmarks that I'm showing for this project, our reference is OpenEye ELF10, the same model that we use to fit force fields. And we compare alongside ambitools in the blue as kind of a measure of what is an acceptable range of charge variance. The basic gist of this slide is that the NAGL models, both of them, perform either comparably or more similarly to, or slightly better than ambitools if we're taking similarity to OpenEye as the metric here. We also ran small molecule solvation for energies in both water and non-aqueous solvents. Again, the performance of both ambitools and NAGL to OpenEye is very similar. And finally, we finished up with some protein ligand binding for energies. At this point, this figure has been shown a couple of times in this conference, so I won't spend too long on it. But the basic gist is, again, very similar performance across OpenEye, ambitools, NAGL. In this case, the first release candidate, but we don't expect the second one to be significantly different. But avoiding some of the issues that you can get with random and conformal generation that you see with ambitools. So one of the main goals that we had with using this neural network is that we wanted to make it easy and fast to assign charges. In this case, NAGL definitely blows all the other methods out of the water, even in comparison to using the template charges, where we just match chemical patterns across the protein. So I just wanted to say that both these release candidates are publicly available for use and for testing. We would really encourage everyone who's interested to try it out, see if there's any issues, and then report those issues to us so that we can improve our models. The easiest way to do this is probably through the OpenFF toolkit, by using the name of the model and using the Naggle toolkit wrapper. There's just one caveat where we've put in safeguards in the toolkit. So if you try and assign charges to a molecule with a bond type that's not well represented in the training set, it will raise an error, and it will tell you which part of it is raising an error. Obviously, you might want to bypass this. So if you really want to assign charges to your funky molecule, you can call the charge model from OpenFF Naggle directly, although of course we can't really say much about the quality of the charges you'll get. So that's it for phase 1 of the neural network charges. I will come back to this shortly towards the end of the presentation and talk about phase 2. But for now, I'd just like to move on to virtual sites and just mention that briefly. So the motivation behind wanting to add virtual sites to our force fields is that our current model of using fixed charge, atom-centered charges just is unable to replicate some of the complexities in the electrostatic potential surface that we know are there. And if we add a virtual particle, then we can start reproducing those features. So for example, the sigma hole around bromine that you can see in quantum chemistry is only really reproducible if you add a virtual site. For the initial phase of adding virtual sites to our force fields, we're just targeting low-hanging fruit. So the sigma holes of chlorine and bromine, as well as the pyridine lone pair. Here is the general fitting workflow that we're using for this. We start off with AM1 charges. We fit bond charge corrections and virtual sites directly to quantum chemistry ESPs. And then we retrain our van der Waals parameters to both dimer energies and condensed phase properties. Following that, we also do one of our standard valence refits, and we get a force field candidate. So I won't spend too much time on virtual sites, but I will just say that we have some initially promising results. So on the left-hand side here, we have plain vanilla OpenFF 2.0. We see that if we just retrain bond charge corrections and van der Waals terms, we see some improvement compared to OpenFF 2.0. But we get much more improvement if we add another van der Waals term to nitrogen. So our current force fields only have one kind of van der Waals parameter for nitrogen. So this is effectively doubling it and splitting out the different chemistries. And it corrects the systematic error that we see with enthalpies of mixing of amine and water, or amines and water. Finally, if we add virtual sites, it's not very clear if you look at the overall data, but if you take certain subsets of the data, adding virtual sites to particular chemistries does improve performance there. So this is, again, still a project that's in progress. We acknowledge that adding virtual sites to our force fields is going to make it more of a hassle to use our force fields. So we want to make sure that the performance increase you get from adding virtual sites is worth it and is worth the trade-off of having to deal with those. So these are the main projects that we've been working on for the past year or so. I just wanted to very quickly mention some of the future things that we have in the pipeline. So specifically, I'll first mention that we have a neural network model now for AM1 BCC charges, but the plan is not to stick with that forever, but to now move on to the next phase, where we can fit the neural network directly to quantum chemistry ESPs at a higher level. And what we hope is that that will improve our electrostatics and result in better performance, but keep the same level of convenience that we see with phase 1 of the neural network charges. And secondly, we plan to start investigating adding or fitting polarizable force fields in the next year. So we realize that's going to make it a lot less convenient to run our force fields. But the hope is that we'll be able to fit a polarizable force field where the increases in performance, again, make that trade-off worth it. So I'd like to finish by thanking everyone who contributed to the work in this presentation. So all the members of Open Force Field, past and present, Open for Energy, past and present especially, all our collaborators and affiliated labs, advisors, the general OpenFF initiative and community, OMSF, and of course, all of you for listening to this talk. So thank you very much.
Any questions for Lily?
Hi, it's me again. My background is as a quantum chemist, and I'm really surprised that you can't do useful charges for large molecules. So I would ask, they will certainly depend on the geometry that you have calculated for the molecule, and that could change them significantly. Bill's done some work on looking at dipole moments of the force fields of the geometries that come from the force field, and compared them with the geometries that come from a proper quantum calculation. And some of the geometries that come from a force field have huge dipole moments. And we think they're unphysical, and we think that maybe some things that shouldn't be extended, they should be folding back on themselves or something. So I don't throw quantum chemistry in the bucket. I would be happy to talk with you more about how one might determine. Yes, quantum chemistry doesn't always work, but that's more about which DFT functional you use and all of those things. And there's a whole stack of questions around that. But I don't think you get huge dipole moments even out of DFT.
Thank you. Sorry, was that a question?
That's fine, you don't have to answer that.
Yes, let's chat after the break. Thank you.
Any other questions?
So unfortunately, Dart and me that you kind of have to tweak with torsions for trying to get secondary structure right, and it makes me wonder, can we expect to do better with kind of incremental change given the baked functional form that is still used under the hood, or should we be a bit more bold and implement something a bit more wacky that gets the physics fundamentally better? And it might take us several more years, right? But maybe in the long run, that's what we have to do anyway.
Yeah, that's a really good question. So obviously, there's a lot of potential in alternate functional forms, and that's something we're very interested in exploring in the future. But the feeling is that there's still quite a lot we can squeeze out of the classical functional form. For example, if we autotype parameters, if we expand our training set, we reckon there's still a lot more improvements that we can get out of this functional form, and it's the one that is most widely implemented, and it's kind of the easiest to use for everyone. So that's probably what we're going to focus on first, but we are very interested in exploring different forms down the line, yeah.
Could we get one more round of applause for Lily?